All right, so tonight, finally, will there ever be another Earth? You are lucky to have Maggie Turnbull, who is a freelance astronomer and an astrobiologist, and we're going to learn more about the potential life on other planets. Maggie Turnbull has been fascinated by planets, stars, and the cosmos ever since she was very young and growing up in Antigo, Wisconsin. And I want to say that Maggie's parents are here tonight, so you can give a little wave and say hi. So, the wonderful parents responsible for this wonderful young woman. Imagine Maggie in kindergarten poring over an encyclopedia of planets. She never missed an episode of Star Trek, The Next Generation. Imagine this, those teachers. I saw a middle school teacher here. In middle school, she read everything she could find on astronomy and tried to share her thoughts on Isaac Asimov's writings with her 7th grade class. She attended UW-Madison and went off to graduate school at the University of Arizona, with stops at Harvard, NASA, and SETI, which is an acronym for the Search for Extraterrestrial Intelligence. Along the way, she developed techniques to identify stars that might have planetary systems, that might have planets suitable for life, creating the catalog of potentially habitable stellar systems. She is now back in Antigo in her new life as a freelance astrobiologist at her own nonprofit organization, the Global Science Institute. She is embracing her new adult life in the Northwoods. She created a farmer's market in Antigo. She learned to make maple syrup. She completed her first Berkey this winter. The hardest ever, I might say, by all accounts. Okay, almost done. So just in time for our event tonight, NASA's Kepler telescope discovered the first the first Earth-sized planet in the habitable zone a few weeks ago. This planet is currently named, believe it or not, Kepler 186f. Now, Maggie Turnbull worked at NASA. She probably knows astronauts. I'm sure she's smarter than all those astronauts. And I'll bet that Maggie has lots of influence over what they really end up naming that planet. Now, she probably can't name it after herself, so I thought we'd give her a hand. Okay, so let's vote on a few other famous figures worthy of the name. Here are a few suggestions that might reveal my age. The first, do you remember Astro? Ruh-roh, the Jetsons dog. Who remembers Hal? Computer from 2001. How about this one? Will Robinson, as in danger, danger, Will Robinson. That was from Lost in Space. How about Yoda? Everybody knows Yoda. And my personal hero, Jean-Luc Picard. Okay, thank you very much to Maggie Turnbull. I'm going to turn things over to her now. And thank you again for coming.
Yeah, thanks so much for having me, and thanks for the intro. So I would like to open it up sooner rather than later to be more interactive, but just to introduce myself, I call myself an astrobiologist. It would probably be more accurate to say that I'm an astronomer who is using the things that I know or am learning about the stars in order to okay, sure, thanks. In order to try and understand a little better how life might be distributed in the nearby universe. And the idea of life on other planets obviously is not new. People have been talking about that and arguing about it and philosophizing about it for thousands of years. But what is new is the ability to really approach it in a scientific way, with a rational method, and actually have real data that we can look at and start to know things about the possibility for life forms that we might recognize on other planets in our own solar system and planets orbiting other stars in our galaxy. And so we're just really at the very beginning of that exploration now. But I think that when humans apply themselves to something, a lot of times problems unfold very quickly, and we have really rapid gains in our understanding. For example, when I went to college in Madison, I started college in 1993, and at that time, 1993 still doesn't seem like it's that long ago to me, but at that time there were no planets known outside of the planets in our own solar system. In fact, at that time our solar system had 9 planets in it, and now we only have 8. So, so but there was a sense that we were getting close. Now I would call them my colleagues. At the time I was just a kid and hadn't met them yet, but there were 2 guys in San Francisco who were trying to find signs of planets orbiting nearby stars, and they wouldn't be able to see the planets directly, but they would be able to tell that the planets were there because of the gravitational influence that they were having on their star just by pulling it back and forth as they orbited around the star. And by looking at the motions of all the nearby stars, they reasoned that they should be able to tell, if any of the nearby stars have planets or not. They didn't have very sensitive instruments, so any planet that they would detect would have to be a pretty big planet, like Jupiter-sized, but still, that would be amazing to know about planets around other stars, because we didn't know of a single one. And at that time, everybody thought that, well, okay, if there are planets around other stars, then it just seems logical that they'll probably look a lot like our planetary systems, with the little ones on the inside and the big planets on the outside. And, okay, great. Well, these 2 guys, after many years of searching and, having talked to them, I know they thought about throwing themselves off the San Francisco Bridge a couple of times, or the Golden Gate Bridge a couple of times, because it was so difficult and nobody would take them seriously. And that's really hard when you're working in a small community of scientists and people don't want to talk to you. But they knew that they were doing good work, that it was rational what they were doing. And the first thing that they found, of course, was a planetary system with a huge planet on the inside. And so in their very first announcement, their very first discovery, they already completely upended everything that we thought that we knew about planetary systems around stars. And the many, many announcements after that have occurred since that time, the first couple hundred were all like that. Big planets orbiting really close to their stars. And so the whole field was in disarray. I mean, the whole field of planetary astronomy was in disarray because it wasn't clear how you would even form a system like that. Our solar system is organized so rationally. It's like we have all the little rocks on the inside where it's warm, and then all the gaseous stuff with lots of water and easily vaporized materials in big planets further out. That makes a lot of sense. Where it's cold, you have the easily vaporized stuff. Where it's hot, you have just the rocky, refractory stuff. And now here there are all these other planetary systems that aren't like that. And so there was the question of, okay, well, now we know that planetary systems are actually pretty common, but maybe we're still rare because their geometry is completely different from ours. But what people didn't, really discuss enough, in my opinion, at the time, was that particular experiment was designed to detect big planets close to the star. That was the easiest thing to see, so that's what they found. Doesn't mean that planetary systems like our own aren't also common there's a lot of stars to go around out there. It just means that when you design an experiment to detect a certain thing, you tend to detect that thing and not a thing that you aren't capable of detecting. So that particular technique of planet discovery was enormously successful, and as time goes on, they're continuing to do that. They are finding, and their instruments are getting more and more sensitive. They are finding planetary systems that are more and more like our own. But our, Jupiter, for example, takes 10 years to go around the sun. So if you want to find a Jupiter-like planet around a nearby star, you've got to look at that star for 10 years. And if you're a scientist, you want to see it go around 3 times before you make the announcement. So that means, 1995, 2005, 2015. In 2025, they'll be announcing all kinds of systems just like our own with that technique. And meanwhile, they'll be building up everything up to that point. But now we also have the benefit of all the information that has come from NASA's Kepler mission. How many people have heard of Kepler? So how many people have not heard of Kepler? And don't feel bad if you haven't. Okay, because I'll explain it. So Kepler is a small space telescope. So it's in space, it's not on the ground, it's in orbit, and it's staring at one particular patch of sky that happens to be very dense with stars. That patch of sky was chosen because in one field you can see over 100,000 stars at once. And Kepler's job, one and only job, was to point at that one field. So you can imagine this telescope in space, and it's in orbit around the sun, and everything's moving. The Earth and the Moon are in orbit, the telescope's in orbit, the sun is there, the whole thing, is moving through the galaxy. And that telescope has such incredible stability that in space, it doesn't move. Its orientation in space does not move for 4 years, just points at in that one exact direction in the sky at that one field of stars, unblinking for 4 years. That was its mission. And its only purpose was to monitor the brightness of every single one of those stars in that field for that long. And any change in brightness during that time would be of interest to us. Because when you have planets in orbit around the star, imagine, you have the solar system, so the sun's in the middle and all the planets are going around. If I take the whole thing and turn it edge on, so that now it appears that the planets are passing in front of the sun from your perspective. When that happens, every time the Earth passes in front, every time Jupiter passes in front once every 10 years, the sun gets a tiny little bit fainter for a few hours and then goes back to its normal brightness. That's all Kepler was looking for that long. And so with a nominal mission, healthy mission lifetime of 4 years, you would be able to see an Earth-like planet go around a sun-like star how many times in 4 years? 4 times, right? If you're a scientist, you're really happy about making that announcement. You feel confident that you've seen it enough times. It wasn't just a quirk. It wasn't just an accident. So Kepler didn't live for 4 years. Actually, I don't know exactly. Somebody could probably Google it instantly. How long did Kepler live? But it was going on 3 years-ish before too many parts broke, and it wasn't able to continue with its primary science mission. But it actually yielded in that time, in that 2, almost 3-year window, quite a landslide of discoveries from that. Quite a few planets orbiting really close to the star that are going around in the course of days or weeks or months, and even all the way up to years. So recently, you can go on the Kepler website and you can see the whole they call it an orrery. It's a whole, a poster with all the little families of planets, and it's even animated, and you can see them all going around their stars, and it's color coded by the temperature of the planet or the size of the planet, and it's really cute. But Kepler's latest fantastical announcement was this system. What's the number again? Kepler 186F. I can't ever remember these numbers. But that, so that is a really interesting system, and I'll specifically talk about that one just for a minute because it illustrates really well the diversity that's out there. F means that that's not the first planet we know about in that system. It goes, the name of the star, and the star is component A, and then B is the first planet, C is the second, D, E, and F. So that means we know of B, C, D, and F. So this is the fourth planet that we've discovered actually in that system. And all of the planets in that system are about the size of the Earth. The star is a faint star. It's much fainter than the sun would be. It's fainter and it's cooler. It's a red. We call them red dwarfs. They're little, very numerous in the galaxy. Most of the stars in the galaxy are fainter than the sun by a lot. Many, many stars are much fainter than the sun. And we name them according to the order that they were discovered. So sometimes, so B isn't necessarily inside of C, isn't necessarily inside of D, et cetera, et cetera. I'm just telling you this completely useless trivia that you're going to pull out at a party sometime. But but F really was the most recent one discovered, and it is in an orbit that is getting pretty long now. I mean, it's like a 8 or 10 month orbit, something like that, and so it's getting to be like what is a familiar size of an orbit to us. But the star is so much fainter that this habitable zone, this zone around the star where the planet would be the right temperature to support life, is actually really close to the star. And all the other planets in that system are closer to the star than planet F. And planet F is quite a bit further out than the others. They're all in really tight orbit, like taking days to go around the star. And then planet F is quite a bit further out. And it's actually, even though it's much closer to its star than we are to the sun, it's actually on the cold side because it's such a faint star. So we think that the planet is in the Hab zone. It would be on the outer regions of the Hab zone. But it's a little bit bigger than the Earth. It's like 10% larger than the Earth. And all we know from Kepler, all we can learn is the size of the planet. We don't know the mass, or the gravity of the planet. But since it's bigger than the Earth, we assume that it's probably more massive than the Earth too, which means it might be able to hold on to a thicker atmosphere than what we have, which means that even though it would be on the cold side of the Hab zone, maybe that thicker atmosphere could keep things a little warmer. But it's an interesting issue because you know how the moon goes around the Earth, and we always see the same side of the moon facing us. You never look up there and see the far side of the moon. You always see that same face of the moon facing us. So as the moon goes around, it's also turning so that always the same face is towards us. Well, that's because the moon is fairly close to us, and that happens when two bodies are close to each other. So for planets in these really tight orbits, they are also probably tidally locked to the star so that their same face always faces the star as they go around it. And that could be a big problem because for these faint little stars, their Hab zone is so close to them, so their planets in the Hab zone are probably tidally locked. That means that one face of the planet is constantly getting shined on, and the other face of the planet, other side of the planet, is continually in nighttime. And what happens is that the near side of the planet heats up from all that light. If there are lakes or oceans on that side, they gradually, they evaporate, they go into clouds, and then they circulate around the planet and they rain out at cooler places. So they rain, and then as more and more of the water evaporates from the near side and goes into the atmosphere, what happens is that all of the water, for example, will migrate to the other side of the planet and condense out into a gigantic ski hill on the other side. So you'll have this like snow cone planet, even if it's in the Hab zone, because it's tidally locked to the star. So, and then after that, the same thing starts to happen to the atmosphere itself, because you've removed all the water from the atmospheric cycle. I mean, we talk about greenhouse gases, when we're worried about global warming, there's too much CO2 in the atmosphere. Well, water itself is a very strong greenhouse gas as well that keeps us warmer than we would be, without water. But if you took all the water out of the atmosphere and froze it into one place on the planet, now, your temperature is going to fall, even more. So once that happens, you start to have a problem where your whole atmosphere wants to condense out on the far side of the planet, and pretty soon you just have this rock with an icy ski hill on the other side. So whether these red dwarfs can even have, we can say, well, they have a habitable zone where it's technically, there's enough light coming from the star to keep it at the right temperature. But if the planet has to be so close to the star that it'll be tidally locked like that, maybe that means this whole class of stars, which is the majority of stars in the galaxy, cannot host life as we know it because of this problem. So the hope is that this particular planet, being a little bit more massive than the Earth, could hold on to more atmosphere, and that atmosphere might circulate more aggressively than what we see on the Earth. And it might be a windy planet, but at least it would be temperate, was the idea. I guess other than that, I can just tell you about a few, so one question might be, well, what comes next? Kepler is over, and these analyses are going, these announcements are going to continue because we're not done analyzing the data from Kepler. I mean, this announcement of this planet F was based on observations that were done with quite a while ago now. So there's still quite a bit of data in the pipeline, and my colleagues are they're really interesting people. Like, they keep finding new ways to discover stuff in data that's already been taken and on the shelf for quite a while. So especially in systems like this, where of several planets, I guarantee you somebody's going to be looking at the dynamics of all of those planets and modeling that and seeing if they can't find evidence for yet another planet that maybe Kepler didn't even see it, but just by looking at the orbits we can tell that there's got to be something else in there. That would not be the first time that has happened. So we'll keep hearing announcements from Kepler data for a while, even though that mission is no longer carrying out prime science. But so then after that, mission-wise, NASA is looking at perhaps flying, this is super preliminary, but perhaps flying a small-scale mission, another kind of mission that would be dedicated to finding planets around other stars. And we're chipping away at trying to get closer and closer to this holy grail of Earth-like planets around nearby stars. And it's great, Kepler, that's great, planets passing in front of the star getting a little bit fainter. Now I know how big they are and what kind of orbit they're in, that's great. But I don't know anything about what they're made of. I can't say anything about if they're really anything like Earth or not. And for that, we need what's called a direct imaging mission. In other words, point the telescope at the star, take a picture, look at the planets. And that's actually really hard because planets are so little and stars are so bright. And the Earth shines in reflected starlight into the universe, but it's 1/10 billionth as bright as the sun. That day side of the Earth shining. You could You could see that from another star system if you were looking back at us, but you'd have to have a really good telescope, and you have to be able to block out the light of the star and see the tiny, tiny little specks of light, that pale blue dot, and block out this blazing light of the sun that wants to overwhelm your image. So we have 2 teams right now that are looking at how you might do that, and the 2 teams were kind of competing with each other, and I think my team is the better team. And what we want to do is fly a telescope, a small telescope, maybe like a meter in diameter. So are there any amateur astronomers in the audience who have backyard telescopes? Okay, how big is your backyard telescope?
130 millimeters.
What's the aperture size? Well, is it like this big?
Yeah, it's about.
Okay, so maybe you have like an 8-inch, diameter. That's how much, the human eye has a pupil, and that's your aperture for collecting light. That's how you see, and it's like 5 millimeters or 8 millimeters or 6 millimeters, something like that. A good backyard telescope, like a good one, that can collect a lot of starlight and allow you to really see some faint things, might have an aperture of like 8 inches, or even like the really souped up ones might have like 16 inches or something. And the ground-based telescopes that we use, like on Kitt Peak in the mountains of Arizona, they might have like 1 meter apertures, or some of them are 90 inches and some of them are like 4 meters across. A 4 meter, that's big. Now you're getting big. Like that's filling up a whole building, for a telescope. And some of our radio dishes are absolutely enormous. If anybody's ever been to Puerto Rico, or if you ever plan on going, I definitely say you must go to the Arecibo radio telescope and get a tour. You have to see it. You can't not see it. It's absolutely enormous. I mean, it takes you 10 minutes or 15 minutes just to walk around the outside of it. I think it's like a whole kilometer to walk all the way around the outside of it. So anyway, and the Hubble Space Telescope is on the order of 2 meters in size. We want to fly a 1 meter telescope, space qualified, good optics. And in front of that, we want to fly a screen to block out the light of a star so that I can see the light of the planets orbiting around it. And it sounds really simple, but anytime you have 2 spacecraft trying to fly with each other in a line, things can get a little tricky. And also the screen has to be really carefully designed to have exactly the effect that you want. But it's called a star shade, and it's the coolest idea ever. And it will, the reason it's so great is because unlike other designs, like the competing team wants to fly what they call a coronagraph, and they have essentially the same screen, but it's inside the telescope, and they say, well, how great is that? Then we don't have to fly the star shade around, and wait for it to get, align with each new target, as we're sitting there doing nothing. We can just turn the telescope and look, and there it is. But my argument is, but you've allowed this starlight to get into your telescope. Like, sure, you'll have a little screen on the inside that'll block it all out from your camera, but that's not how things work in the real world. In the real world, there's always some little flaw in the engineering, or little dent or scratch or piece of dust or something, that when you allow the star to shine on that, it will scatter starlight all around, and it'll get right past that screen, and it'll land on your image, and it'll look like a planet. And then you're going to spend the next 2 months taking spectra of it and studying it until you realize it's a piece of dust. And the screen is these are the kinds of discussions we have all day, right, in my field. But if I fly the star shade, then the telescope, the whole telescope is inside this deep shadow. And I can just sit in there and no starlight gets into my telescope. Like nothing can happen. Nothing can go wrong. I just have this beautiful dark image, and every single thing that shows up in my image is real. So anyway, we have this little friendly competition going on, which is actually not that friendly. But we just submitted our halfway through report. It's a 1.5 year study. We just submitted our interim report, and those are now posted online. And I actually think that even if you're not an expert in the field, I actually think those reports are kind of interesting to look at. And they start with an executive summary. I mean, I posted it on Facebook because I thought that the way that it's written is accessible, to everybody. And it kind of has to be, because the people who work on these things are coming from so many different backgrounds that we don't even necessarily speak each other's language that well. So it has to be written in a way that a broad audience can understand. But those are now up on NASA's Exoplanets website, and you can look at those interim reports for our Starshade study and the coronagraph study for finding Earth-like planets. I'm going to stop blathering on and take questions from anybody who wants to ask.
Okay, I think we're ready for questions. Adam, are you ready for sprinting?
Yes. Well, I'm going to walk here. Anybody? How about up top? No.
I have a question.
Oh.
If NASA technology were at another planet so many light years away looking at our solar system, does our sun wobble
Yes.
enough to be detected?
Yeah, so
Repeat the question. Sorry.
The question was, if NASA technology or current technology were at another star system looking back at us, would it be able to see that our sun wobbles too? And absolutely yes, it does. The sun has, in addition to its path through the galaxy, it has a little curly Q path thing that it's doing, because all of the other planets are, as they go around the sun, they're exerting gravitational force on the sun, and that is pulling it back and forth. So we would be able to see that, from another star system.
In light of the talk about cutting back on space exploration that's being bandied about, what do you see? What do you forecast? Not what you would like to see, but what would you forecast as the reality of exploration as coming in the next X number of years?
So a couple of years ago, I wrapped up a study and published it, wherein I slaved away for 4 years on developing a design for what we call a flagship mission. These are big, very capable missions along the lines of Hubble or the James Webb Space Telescope, which will be the next one up after Hubble, to do what I want to do. Basically, a big telescope with a star shade that would not only be able to detect Earth-like planets, it would be able to find oxygen and plants and water and carbon dioxide and all these interesting things, and it would be able to do it for hundreds of nearby stars. That's a flagship mission. I think that the era of flagship missions is coming to a close. I think we might be done now after JWST, with flagship missions. And I have no tears in my eyes saying that. I actually think that that's fine. I think that if we can get a little more focused with our priorities and move forward on smaller scale missions that accomplish more specific objectives, that's not necessarily a bad thing. The thing that we saw with JWST is that it almost destroyed NASA. And I'm making this sound like really sensational and bad, but in my view, there were a lot of management problems. It was just so massive. There was a lot of cooks in the kitchen, and there were a lot of management problems, and it was mismanaged, and communication wasn't occurring the way that it needed to, and people were overstating how much bang for the buck they were really going to be able to get out of this mission. And at the end of the day, you just feel like if your particular interest is not represented in one of these big flagship missions, too bad. You just have to sit there and wait for 2 or 3 decades until we're done with that. Whereas if you could fly smaller scale things that don't take as long to get off the ground, we'd all love to have our own 10-meter space telescope, but we're not there yet. Maybe we will be with the help of private funding. If you get some big donors that get interested in this and want to be the first one to do X, Y, Z, there's nothing stopping that from happening. Could happen. But when you're talking about a large government agency trying to invest so much of its resources in one particular mission, I think that's what we are learning from JWST, that's also very vulnerable to massive problems. So James Webb Space Telescope, don't even get me started on the naming of these things, but so it was a heart-wrenching thing to watch, but the outcome has been that I think we're learning really valuable lessons from that, and I hope we don't have to repeat them. That maybe flagships are over for a while, but that's not necessarily all bad. Rick?
So that means we probably shouldn't hold out much longer for our jetpacks. But that wasn't my question. So I was wondering, how far away are some of these planets that you're talking about in terms of time?
Oh,
and the light that it takes to
actually,
get there.
I'm glad you asked that, because I think, when we're growing up and we're in grade schools, one of the things I think that teachers try to impress upon kids is how far away everything is. And I think that people come away believing that everything is millions of light years away, and that all the stars could be burned out and we wouldn't even know it because they're so far away. Not true. The Kepler stars, because it was pointing at that one field that is so densely packed with stars, it's basically looking through a tunnel where there just isn't a lot of dust and gas obscuring the view towards the center of the galaxy. So most of those stars actually are pretty far away, on average a few thousand light years away. But a few thousand years, that's, to an astronomer, a few thousand years, that's nothing. That's those stars are all alive and well. Stars take billions of years to die, so those stars are good. But the Kepler stars are very far away. The other method I was talking about with the wobble, those targets are much nearer to us, within 100 light years even, or so, most of them. So that's, they're not very far away. And the stars that I'm talking about looking at with a star shade mission, these are all naked eye stars. These would be 30 stars that are practically in our backyard. Anybody could walk outside. They're the brightest stars in the sky. And just see them, with your eyes. And those are not any farther away than, I believe the farthest one away is about 10 or 12 parsecs, which is 30 light years away.
Maggie, can you remind people what a light year is?
A light year is how far light travels in 1 year. So light travels about 8 inches in a nanosecond. and it travels a really long ways in a year. There's no point in even throwing out these enormous numbers because nobody knows what they mean, including myself. So but the nearest star to us is about 4 light years away. So if we traveled at the speed of light, it would take 4 years to get to the very nearest star to us. Yeah.
I think a light year in miles is close to 6 trillion miles.
There you go. So if you know what 6 trillion is, that's how many miles a light year is. It's incomprehensible, really. So we just break it down. We put everything in units that we can use small numbers for. The nearest star is 1 parsec away. I don't know if I should really be pointing at people. Maybe I shouldn't be
Okay,
moderating.
I had a question.
Okay.
I'm curious, is there any parallel or similar findings from what you see in the big telescopes as what we see in these nuclear accelerators smashing atoms today? Is there any similarities to what you find?
Well, they're very different kinds of experiments, but ultimately everything is connected. I mean, this is the universe we're talking about. It's not like the universe has one compartment over here and then another compartment over there. In terms of like the magnitude of the breakthrough, I would probably argue that finding an Earth-like planet around a nearby star is, at least in an immediate sense, more impactful than the discovery of the Higgs boson, only because when I walk around every day and conduct my affairs, I don't really care to know about the Higgs boson. Like, that's not useful, it's interesting, but I think that when we have a list of nearby habitable planets that we can point to, even if it's just one, maybe it'll be like 5, then that's actually going to be important to people, because when you have a list of planets that could potentially support life as we know it, I think it's only a matter of time before a whole new section of the economy arises and people are building spaceships to seriously try to travel between the stars. I mean, I actually believe that. And I know it sounds a little far-fetched, but DARPA, which is the research wing, sort of the R&D wing of the Defense Department of Defense, is actually supporting an effort right now to develop a spaceship with people on it, leaving the Earth and traveling to other star systems within 100 years. They're calling it the 100-year Starship. And that effort is being led by Mae Jemison. She's an astronaut. And she she's trying to figure that out. Like, how would we develop a community of people who was continuously working toward that goal and answering all of the difficult questions that need to be answered, so that we have people on a starship leaving the Earth and going to other planets in 100 years. And my answer to that was, all you have to do is give them the list of destinations. If you give them a list of destinations, people are going to want to go. So that's why I think Earths are better than the Higgs particle.
Maggie, I had a question about tectonics in life. Seems like it's not just temperature that's important for habitation, but a planet has to have active plate tectonics.
Yeah, there's so much more to the equation than just how far away the planet is from the star. And tectonics is a good example of something that's essential for life on Earth that might not be present on another planet that is approximately the size of the Earth. And we wouldn't be able to know that from Kepler data. I mean, Kepler is telling us the size, but again, nothing about the composition or the structure. With direct imaging, if I could tell you about the atmosphere, now I can say something about plate tectonics, because one of the reasons why we have the atmosphere that we have is because the movements of the Earth's crust and the volcanoes that erupt, and the way that the atmosphere interacts with the exposed rock, and weathers out, that reaction that happens between the air and the rock, takes CO2 out of the atmosphere, and then plate tectonics will subduct that down deep into the Earth's crust away from the atmosphere. And then meanwhile, volcanoes are erupting and pluming out other kinds of gases, greenhouse gases, and the whole atmosphere is being recycled in that way. And actually, it's being maintained. You know, our greenhouse situation has been maintained for billions of years here because there's a balance. When you have a lot of CO2 building up in the atmosphere from volcanic activity, the atmosphere reacts more vigorously with the rock and takes it out more quickly. And if you have a lot of weathering going on and it takes too much CO2 out so that the atmosphere cools down, well, then that weathering slows until volcanoes can build it back up again. So we've had these big temperature swings throughout the millennia, but overall, the Earth has been able to sustain a habitable climate for billions of years because of this cycle going on, this rock cycle, atmosphere and rock cycle that's going on. But Venus, meanwhile, does not have, I mean, this is a planet very similar in size to the Earth, does not have plate tectonics. So why would that be? And it could well be that Venus, the problem with Venus is that it's so close to the sun that the water all evaporated into the atmosphere, and there wasn't enough buoyancy there wasn't enough water in the ground to create buoyancy so that there could be crustal plates moving around. There's a lot of different ideas about that, and it's not really worked out, why there are such extreme differences between Venus and the Earth, but that's a good example of something we can't know based on the data that we're able to collect right now without direct imaging.
Mars used to have some plate tectonics, right?
The comment was that Mars used to have some plate tectonics. Well, there's an enormous shield volcano on Mars that indicates there's volcanism. Certainly there was volcanism of some sort. Whether there were individual plates that moved around for any significant amount of time, unclear.
Maggie, there's a question behind.
Yes. In our house, we have a beautiful picture of the Earth taken from outer space. And I think at the time that picture was taken, there was a thought that once humans on Earth saw us floating a little island in space, that we would get together and be more peaceful. What do you think the impact would be if we could prove that there is life on another planet for us humans living on Earth?
So I think that the picture you're talking about is of the fully illuminated Earth, and it was taken by the Apollo astronauts on their way back from the only Apollo mission that happened to be in a geometry so that during its return from the moon to the Earth, the sun was directly behind them, and so the entire face of the Earth was illuminated, the blue marble picture. And I think that was Apollo 8, and that was the only picture of the fully illuminated Earth in existence for decades. I mean, that was like the single most reproduced image ever in the history of humanity taking images. And now we have satellites in geosynchronous orbit that are far enough away and have a wide enough field of view they can get the whole planet at once, and so there's lots of choices now, but that was the one. That was the only image for a long time. And I wonder, I feel like sometimes these things soak into the collective consciousness in really subtle ways that are, it's not like this image comes up on the screen and then now society is different after that. It takes a while for that to be absorbed and to have downstream effects. One person here is really strongly affected by that, and after a while they have an idea to do something that was ultimately inspired by that image, even though they might not even make the conscious connection, and pretty soon you have a whole movement towards, recycling, or you're, stopping deforestation or something that may have been catalyzed by that one image, but it takes a while for these things to show up, as a change of consciousness in humanity. And the discovery of life on another planet, I've thought about this a lot. In fact, I was thinking about it today. I'm supposed to be writing this article that's just like, how do I articulate something that I don't know anything about? But what kind of impact that would have on us to know, if there was an announcement next week that we definitely have definitive evidence for, microbes that once lived on Mars, versus an announcement that we have definitive evidence for microbes that are currently living on Mars, versus we have found fossils of fish that used to live on Mars, versus we have found a planet around another star that appears to be supporting an entire ecosystem, including photosynthetic life forms of some sort. And that's something that we would be able to see in theory. Plants have a very distinct signature that even if the Earth was just still a speck of light and you wouldn't be able to see continents and oceans coming in out of it, you could still detect them because plants absorb very strongly at optical wavelengths and then suddenly get really bright in near infrared wavelengths, very reflective. And that signature is used by Earth sensing spacecraft to monitor the health of vegetation all over the world, for example. But anyway, that's something you can detect across the universe. But so I think that those different kinds of announcements about life on other planets might have different short-term reactions. But overall, like once, over the course of a decade or a couple decades, once that soaks in and a new generation of people is born, knowing from birth and just taking it as old hat, that there are alien civilizations living on some planet around that star over there, and are we friends on Facebook? Or how can we how can we get over this annoying time delay where I send a message and have to wait 4 years for them to get back to me, or 8 years round trip, So the way that I've seen young people absorb new ideas and new technologies that might have seemed unimaginable even to me in my childhood, which doesn't seem like that long ago, I think that that kind of news, as shocking as it might be in the short term, would become just regular for the generation after us. And then I do think though that it would change the economy. I do think that people would start wanting to go out, especially kids, who are interested in science or whatever. Well, I want to go to that. I want to see what the forests are like on that planet and send a probe or something.
Can I take a quick interruption and see how many more questions we have in the audience? Just raise your hand if you still want to ask something. Okay, we got a few. Okay.
Do you want to continue with questions?
I'm sorry, just one more time, raise your hand if you still have a question. Okay. We still have a bunch. I'm going to give everybody just a 5-minute break, not long, and we'll let Maggie catch her breath, and you can get another beverage. We'll be back in 5 minutes. Thanks. Okay, I think we're ready to take another question. Adam, are you circulating?
Yeah.
There you go. Okay. Oh, we've got this fellow has a question. Okay.
I just wanted to ask about Molten Core, because I think I've heard that since Mars doesn't have a molten core, doesn't have a Van Allen belt, so that it can't hold atmosphere. And I also wondered if not having a molten core maybe makes it so that the moon is oriented in that one position, always facing us, because it's always off balance. Like Mercury is, it's always off balance, so it's...
Right. Well, this is another good example of how more than just the distance between the star and the planet comes into play when you're talking about being able to support life. the size of a planet, if a planet is very small, A, it's not going to be able to hold on to a lot of atmosphere, and B, it's going to cool off quickly. Planets, when they're formed by lots of debris coming together and big impacts, and temperatures are really high and everything's molten, and then things cool down and solidify. But the Earth is not done solidifying yet. It's been cooling down for the last 4.5 billion years, and there still is heat coming out of the Earth's crust. That's hydrothermal activity at the bottom of the ocean, for example. And that's a really important part of what makes plate tectonics possible. It's why we have a living planet. It's not just that we live on a planet that has life on it, it's that the planet itself is still alive as well, alive as in active. And that's because it has a molten interior, and there is still heat escaping from the planet. Mars, being a much smaller planet than the Earth, cooled off much more quickly. Probably not much of a molten core at all. Its magnetic field is not active like ours. It does have a magnetic field, but it's kind of frozen into the planet the way that when things cooled down and solidified, that's it. That's how your magnetic field is forever then. Whereas the Earth's magnetic field is moving around and even flipping, north and south poles flip every so often, and some scientists even think that we're due for another flip. So if you notice your compass is all pointing south, sometime soon you'll know. Sometimes when I get really confused with directions and I'm walking the exact opposite direction I thought I was, I wonder if the magnetic field flipped and my internal sense of direction got messed up. If you see all the birds, flying north for the winter, you'll know something is up. But that happens because the Earth is still itself, a living planet. Did I answer that question? I feel like I did. But and the moon too, cooled off. It's basically just a rock, and it's solidified in a way that was not completely symmetric. So there are anomalies. There are little mass anomalies on the inside of the moon, and the near side of the moon has in there somewhere. There's some heavy chunk of something that solidified off balance, and that's why the moon is tidally locked to the Earth. That's going to happen. If you're too close, it's going to happen. In the case of Jupiter's moons, Jupiter's moons are small. They're smaller than the Earth, but they are still active. And the question would be, why is that? So Jupiter has a tiny, bunch of moons. He has 4 big ones. The innermost one is called Io, or Eo, depending on how you want to pronounce that word. Io is how you spell it. And it's it's the most volcanically active body in the solar system. But it's because it's so close to Jupiter that, yes, it's tidally locked, but it's also being tidally deformed and massaged and kneaded by Jupiter's gravitational field as it goes around that big, massive planet. And so you can watch movies that NASA has taken. The Galileo mission that went to Jupiter to explore these moons, and Jupiter itself made movies of these volcanoes erupting and these plumes coming up off of the surface of Io. It's fabulous. I think they're some of the best movies ever made about other planets. But then a little further out, you have the moon Europa. From an astrobiology point of view, the moon Europa is probably the most interesting place in the solar system. It also, by now, should have cooled down and solidified into a ball of ice, mostly ice. As you go further out in the solar system, all the bodies become more and more icy and have more and more water on them. In fact, we wouldn't really expect a planet as close as the Earth is to the sun to even have much water on it at all. And if you separate the water out from the Earth, there's just only a little bit of water on Earth. There really isn't that much water on our planet. And the water that is here was delivered to us from further out in the solar system by asteroids and comets that impacted the Earth long ago. So our oceans did not form with this planet. They were delivered later on. It's kind of an interesting thing to know. And some of that delivery and those impacts occurred because Jupiter is out there and was stirring things up and threw a lot of material, that icy material, in toward the inner parts of the solar system where you wouldn't expect to find it. So that's why we have oceans on Earth and fish and life. And Jupiter's moon Europa is an icy body, and it's close enough to, it's not so close to Jupiter that like Io, it's nothing but a bunch of volcanoes, but it's still close enough to feel some of that tidal warping and massaging. And so what you see is this icy moon with this crust all the way around, icy crust all the way around, huge fractures and crisscrossing crevasses all over that are changing over time. And the Galileo orbiter found that Europa is most likely actually an ocean-covered planet with a shell of ice floating over the top. And with that kind of tidal heating, we call it, it's likely that there could be hydrothermal vent activity as well under the ocean on this moon. So that also is a living planet. And from the point of view of life, that means that there's interesting chemistry happening and potentially a lot of interesting metabolic pathways that could exist for life forms. There's not any clear way to have oxygen in that ocean. I mean, it's expected that it would be an anoxic ocean, which might not be good for large life forms like what we see swimming around in our oceans here. But then again, what do we know? You know, sometimes there's a lot that goes on in the universe that we do not know about until after we see it. So, so a probe, if I was going to send a probe anywhere in the solar system, I would send it to Europa, and it would have a hot drill that would just, like a hot water drill, actually identical to what we use in Antarctica to drill through the ice for science experiments there. Hot water drill, drills through, falls through the shell, deploys a little, it has to be artificially intelligent swimming probe of some kind that can go swim around with the camera and decide where to go and avoid the sharks and whatnot, and then send all the data back to Earth for us to look at. We can't have, it has to be artificially intelligent because the time delay in communication is too long for us to, if there's an emergency, for us to tell it what to do. So it has to kind of know how to stay out of trouble, and how to seek out interesting things. But I think that would be the most fantastic mission that NASA has ever come up with, if we could do something like that.
I'm wondering, you were talking about greenhouse gases and the difference between Earth and Venus. I'm thinking about climate change and wondering if you see life on Earth as particularly fragile, not just in the sense of like whether our society and culture will be here, but whether life in some form is very vulnerable.
Yeah, I think it's a really logical thing to then think about climate change when you're discussing that part of how we have our climate on Earth. And when I teach about the planets, that's where I put the climate change discussion, because it makes a lot of sense. I don't see life on Earth as being that fragile. I see human life as being incredibly fragile, but I don't see life on Earth as being that fragile. I think that no matter what we do to ourselves and to the forest and to all the large animals in the ocean and on land, once that stops happening, either because we're gone or we suddenly get really smart, life is going to go on in new forms for quite a while on Earth. I don't think it's that fragile. We find life living in really extreme environments all over the planet, including many environments that have, as far as they're concerned, they have no idea, A, that we're even here, and B, that the sun shines. I mean, there are communities that live at the bottom of the ocean that if the sun went out and the oceans froze over, would continue right on happily living off of geothermal heat for, I don't know, the next 500 million years or billion years even. But, the Earth itself is, the Earth right now is kind of at the inner edge of the Hab zone, which I find really interesting because we're on the hot side to begin with. And, the Earth goes through these cycles because of its orbit, little shifts in the orbit, and we're already in a warm period. And so then to add on top of that, huge amounts of greenhouse gas when we're already not in an ice age, it's an experiment that if I was just this cold, unfeeling scientist looking down from above and watching it, I'd actually be very interested to see how that would go. But since I live here, I'm troubled. But the Earth so it's already at the inner edge of its Hab zone, and the interesting thing is that stars, as they burn through all of their fuel, they get brighter over time. There's physics behind that. But the stars gradually get brighter and brighter and brighter. And so the Hab zone around the sun is gradually moving outward. It's just slowly marching outward. And meanwhile, the planets stay where they are for the most part, and unless something catastrophic happens, but they pretty much stay where they are. And so within the next 2 billion years or so, the Earth isn't going to be in the Hab zone anymore. It's going to be inside the Hab zone. And I remember like the exact day in grad school and where I was in my house when I realized this, and that we only have 2 billion years to go. And I know that I know that 2 billion years is a long time, but we're 4.5 billion years in. And all of the things that have happened on this planet, I mean, just, the dinosaurs, for example, and all of the different kinds of life that have risen and fallen and risen and fallen, and all the different things, so much of that is preserved, or at least little bits and pieces of it are preserved in the rock record, so that we kind of know that story a little bit. And now we're here, the dinosaurs are long gone, except for the birds, the songbirds, and interesting other birds are still here. But we're here, and, maybe we'll kill ourselves off, maybe we won't. But there's going to be life, after that. And then in 2 billion years, the Earth is not going to be a habitable planet anymore. And it's done such a good job for us. And it's been so productive and really just beautiful. It's hard for me to imagine that it's going to be the sun that ultimately draws the curtain on us. And when that happens, the Earth will hang out, for a while, not being a habitable planet anymore. And then eventually the sun will just run out of hydrogen fuel to burn, and it will start burning helium fuel instead. But that's a whole new phase of a star's life. And at that point, it swells up to the point where the Earth will be orbiting inside the surface of the sun and probably just dissipate into the atmosphere of the sun. And at that point, actually, Europa might become a pretty comfy place to be. But I still feel like I just remember realizing that and realizing how much time we had. I mean, we're more than halfway through, and from a cosmic perspective, kind of almost nearing the end for the Earth. And it's like, well, who's gonna ever know? Like, we wrote all these books, and we made these things. We flew in airplanes, we had spaceships, we had people that went to the moon, and we had people that were inspired, and people that helped each other and tried to feed the sick and the poor and tried to save the animals, and people who just had all of these things that they cared about, and maybe some of it got written down and maybe it didn't, but it doesn't really matter because in another 2 billion years, nobody will know about that anymore. Nobody in the universe will know, other than the fact that we are emitting radio signals right now that will continue to travel out into the universe. And so, we're kind of probably going in the direction of radio quiet now, where that will stop. But there will be a good, 100 years there of radio noise that will be marching out through the galaxy that other astronomers might pick up and learn from for a while. So maybe our record won't completely pass from the universe, but it's just, it's an interesting thing to think about. Yes.
Well, that's kind of a little segue to my questions. I actually have two questions. One is a little bit non-technical. It's more of like your gut feeling, and the other is a little more technical. You must be doing all this because you have a sense or feeling that there is life out there somewhere else other than Earth. So that's like, what is your gut feeling about that? The other one is a little more technical, but we think of Earth and we think of life as being just carbon and oxygen based. But what are the other elements that could actually support life in the universe besides those? We think of, you just mentioned about like the oceanic trenches where you've got organisms living that have nothing to do with photosynthesis, has nothing to do with, carbon systems. So what are those, on the technical side, what could be the elements that could be out there being signatures for life? You may not have to see the planet, but you could see the distribution of elements through the universe and where are the highly concentrated ones, so to speak. So what is your gut feeling first on life out there, and then the technical part?
Well, I would say gut feeling wise, I kind of have this simultaneous mental posture of don't know, and it's got to be out there somewhere, because just the diversity of environments that are inhabited by something on Earth. I mean, you almost can't go anywhere on Earth without finding some creature that is managing to survive even in the most hostile environments. And not only that, but the way that organisms network with each other to make very inhospitable environments suddenly habitable is fascinating to me. Like if you go to the Atacama Desert and look, there's a region of the Atacama Desert, this is in Chile, it's in a double rain shadow. No matter which way the rain tries to come from, the mountains get in the way. And it's called the Yungay region of the Atacama Desert. It's probably the driest place on the planet. They get like a little gentle fog every 100 years or something like that. And as a result, you look out on this landscape and it's just desolate. And nations have waged wars over this part of the desert because it's so dry that when nitrates precipitate out of the atmosphere, like because of lightning, that normally comes out of the atmosphere, lands on the ground, and little creatures eat it all up. It's like fertilizer, just greens everything right up. And when it's in such a dry environment, though, nothing can really live. And so these nitrates accumulate, and they're the basis for fertilizers and explosives. And nations have literally waged wars over this most inhospitable part of the planet because of these massive nitrate deposits. And you can see these little pieces of just white stuff sort of laying all over the place. And what's interesting is if you pick up, this sort of translucent white stuff, or there's also quartz deposits laying around, what you can see is that these translucent rocks will sometimes have a little thin layer of green algae living underneath them. And that is a sheltered little environment where the light can filter through the rock, and that 100-year fog that comes through is just enough to create kind of a humid environment for these little things to like make a living on. And when when these algae, little microbial algae bodies die, they fall into the soil underneath, and there's other little things that eat the algae, these microbes that eat the algae, that live underneath that stone. And that's the only place they live. They don't live in between the stones. They live under that stone. And when you move that stone, you've destroyed an entire little ecosystem. So put it back. But it's like, if you can have that on Earth, I think that it seems to me that we shouldn't really actually be that surprised to find life on other planets elsewhere, especially in our own solar system. I mean, there's been so much exchange between the planets. If we find life on Mars, I think our going assumption should be that we're related. And I think we don't even know for sure, if there is life on Mars, or was at any time in the past. I think we don't know whether it got started there and came here, or whether those were two independent events. But we shouldn't be surprised at all if we find out that we're actually related, or even that we came ultimately from Mars, because Mars definitely would have been a habitable environment in the ancient past. We know that for sure. There were rivers and lakes and seas on Mars, and being a little farther away from the sun might have been to Mars's benefit. The young stars are very active and can be difficult, like many of us when we're young. But so, okay, my gut feeling, yes, I think that there has to be some kind of life. As far as alternative biochemistries, there are books about this, or at least articles I know that some of my colleagues have written, and I'm not an expert in that, but I do know that no one has come up with an alternative biochemistry, an alternative to the carbon and water that's as awesome. I mean, water is this fabulous substance that has a huge range of temperatures over which it remains a liquid. I mean, all the way from 0 to 100 degrees Celsius. That's a huge amount of energy that you have to put in to go from being ice to being gas. And in between, you have this wonderfully enormous range of temperatures where it's a liquid, and it's just the perfect medium for all these different kinds of reactions to occur in it. And water is also a polar molecule, so it interacts, a great solvent, but it's also a great medium for a lot of different kinds of chemical interactions to occur. And then carbon forms these incredible structures as well in water, and works with so many other kinds of elements that you can create. Your body is literally full of these little machines that walk around and care. I mean, I learned about that in grad school too. You just can't even believe all the little structures and molecular motors and things that are able to form with water and carbon, basically, and a few other add-ins. But others have explored, for example, maybe ammonia. Saturn's moon Titan has a whole weather cycle that's based on methane and ammonia, methane-ethane oceans. Maybe that could be a medium for some kind of interesting chemistry, but it doesn't seem to work quite as amazingly well as water. But again, our knowledge is just so limited, and sometimes we have to just discover something in order to realize that it can work.
My question is, when I wake up in the morning, I make some coffee, I look at my email, I have my to-do list, bring out the garbage, go to the post office. What's on your to-do list every day? It sounds a lot more amazing than mine.
Pretty much all the same things. But I also have a lot of telecons with scientists and engineers all over the country, and I usually have some number of plane tickets in the queue of meetings that I need to get ready to go for and try to be prepared for, and spend my day looking at, either trying to write articles about things like this, which causes me to have to do a lot of research so that I can know what I'm talking about, or looking at data and trying to come to new conclusions. This study that I've been on with the star shade has given rise to so many little questions that I've never considered before. And a lot of it just has to do with how you go about detecting and then knowing that you've detected a sign of life or a sign of anything interesting on another planet. And so I spend a lot of time looking at spreadsheets.
How many planets can live in a habitable zone around a star? How many is 8 planets like we have around ours? Is that considered normal or a little peculiar? And third, what do you think of the Cosmos series on on Fox?
That's right. I thank you so much for also giving me a little note with those questions, because I meant to get to that, and thanks for asking again. So can more than one habitable planet exist around one star? I think absolutely yes. There's no reason to think that could not occur. The sun, as I've mentioned, is relatively bright. It's a relatively bright star compared to the vast majority of stars in the galaxy. And that means that it hosts a habitable zone that is a bit wider than what would be the case for a fainter star. So the hab zone not only moves outward as the star gets brighter, but it also gets physically wider as it moves outward. And so that means you could fit more orbits in there. Now, brighter stars don't live as long, so there's a limit to how bright you want to get with a star that you live around. Stars that are even like twice the mass of the sun aren't even going to live, a billion years. So they're already swelling up into this, red giant state that I talked about before planets are even completely done forming. So there's only so big of a star you want to be around. But the sun could have had 3 habitable planets. If you swapped, some people have said if you switched Mars and Venus around, we could have had three habitable planets in this system. And then also, it kind of depends on what you mean by habitable planet, because Europa, for example, could have life on it right now, and then that would be 2 habitable planets in our solar system. And Europa's not even in the hab zone, but it's in orbit. It's a moon, in orbit around a giant planet and being heated from the inside. So that's kind of a different kind of habitable. We call it a tidal habitable zone. That could be anywhere in the system. It doesn't have to be at any particular location around the star. So definitely yes for that one. And your second question was, is 8 planets around a star a lot of planets or not that many? It looks like, so we're just at the beginning of this discovery, but it looks like multiple planet systems are really common, and we're not quite up to knowing about 8 planets around another star yet, but that's not because they aren't there, that's because we don't have the data yet. And so amongst the stars that we've looked at long enough to discover multiple planets in them, we're seeing them. It's not rare. So I guess time will tell on that, but it doesn't seem like 8 planets is a huge number, compared to what other stars might have. And then what do I think about the new Cosmos series with my friend Neil Tyson? Has anybody seen it? Okay, and it's thumbs up then? Yes? Okay, well then I love it. Because that's for you guys, that's for people who, aren't like drowning in this field of research like I am, to enjoy and benefit from everything that we're doing. There's just no point in doing any of this if we can't all be participating in some way. And so I'm really glad that they revived that series and they're doing it. That said, if I was doing it, maybe I'd do it a little differently. I don't know.
I have a question right over there.
All right. I feel that the Cosmos series is a good start, but what do you think would be a good way to galvanize the nation into space exploration and scientific, like pushing towards more scientific research, like similar to the way that the Apollo mission did in the Cold War?
Well, I say discovery is the way. You know, you gotta work with what you have in order to do anything. You gotta work with what you have and use it. You know, find a way to work with what you have to make a meaningful discovery, and then that will galvanize the field. But I don't think there's any amount of like just rah that we can do to change the landscape that much, because there's rah about a lot of things right now, and sometimes it's hard to argue that what I'm doing is more important than millions of other things that need to be happening right now in our nation. So I'm actually pretty happy with the way things are going. I feel like the balance, even though, you know, probably most scientists would say, oh, we need more funding, blah, blah, blah. Everybody is saying we need more funding for whatever your thing is that you want. So I'm happy that we have a space program and that I'm able to do this kind of work. It's kind of amazing, actually, to me that this can be my job for real, and I can actually support myself doing this. Because the only reason I can do this is because everybody else is doing the thing that they do that keeps the economy running, and we all, you know, at least there's enough interest collectively amongst ourselves that some of us can do this kind of work. But it's not the kind of thing that rakes in big bucks. So to me, that means that I'm happy to be able to do it at all, you know, because in some ways I'm not pulling my weight by generating, you know, large amounts of wealth for the nation by doing it. But it's you never know where it might lead.
Excuse me if I missed. I was gone for a couple minutes during the question and answer period. So so you might have addressed this, but the question had to do with you answered a question about tectonics, and you described an interaction on Earth about tectonics and these chemical reactions, you know, with atmosphere and rocks that influence the chemistry of the atmosphere and global warming. And it was just a whole nother layer to this, you know, problem or issue that, you know, than I've heard. So given you know a bit more about this subject and the complexity, how do you see the seriousness of this man-made carbon dioxide and other warming gases that are, you know, that are certainly in play in the
Yeah, we did have a question about that while you were gone, and that if, you know, I said that, you know, I think it's pretty serious. You know, this is basically, if I could just boil it down to one thing, there are natural cycles that occur over the course of millions of years, and we've been in and out of ice ages in warm periods before, and life has been very impacted by that before. But the situation now is that we're not in an ice age. We're in a warm period, and then we're adding on top of that, you know, a tremendous amount of greenhouse gas to the atmosphere. So I think it's an uncontrolled experiment. We're doing an experiment with our planet as the laboratory, and that's an uncomfortable position to be in. But you know, I guess we'll just see how that all unfolds.
So I want to go back to the anecdote you had about Chilean desert and the nitrate lump pile stones that have the little bit of life under them, the little bit of algae life under them, leading to a little bit more life. And you said, you know, if an environment like that can support life, heck, maybe environments on other planets that are similarly harsh can support life. And I was thinking to myself, and I would be surprised if a lot of people in this room weren't thinking something similar, something along the lines of, well, okay, if that kind of life exists on other planets or other places in the solar system, that's great. But like, Maggie, we're talking about aliens. Like, we want the aliens, right? So what I mean, my question is there a difference for people like you and scientists like you between life that exists in form of algae or bacteria or something very small or microscopic, and everyone's thought of aliens as people with one eyes or green skin walking around? Or to you, is it all just life? Hey, we've got life on another planet, that's great. Or is that a meaningful difference between the two? Does that question make sense?
Yeah.
Yeah.
Well, I want aliens too, and I did my dissertation. I started working with SETI. I just thought, when the movie Contact came out, the only reason I'm here right now is because the movie Contact came out. And I was still in college at the time, but it had a major impact on where I thought I was going with my career. I'm not kidding. It was that movie. And I went to the movie ready to just pan the movie because I was a junior in college. I was doing my summer at Harvard. I was going to know everything that was wrong and inaccurate in that movie with regard to space and how they portrayed it. And it did start out, that opening sequence, I don't know how many people have seen the movie or if you remember this, but that opening sequence, where they're zooming out of the Earth and going by all the other planets and eventually through the galaxy and then out of the galaxy and out to the edge of the universe. And then meanwhile, you're hearing the radio signals from the Earth going back in time as you go farther away. I thought that was such a cool way to portray that, but they had the timing all wrong and I noticed it immediately. They were for some reason we were out at Jupiter and hearing shows from back in the 50s, and I was like, the solar system isn't that big. But by the end of the movie, I was pretty much standing on my chair saying, that's what I'm supposed to do. And so then a year later, there I was working with Joel Tarter at the SETI Institute, and I ended up writing the first half of my dissertation on how to choose targets for the search for extraterrestrial intelligence. And I still am close with that group of colleagues and maintain ties, although my work has evolved to go in the direction of detecting Earths. I think that's, we can't not do that. Why would we not listen for alien signals? I mean, it's the cheapest experiment you can do. It costs nothing. You just need time on a radio telescope, and you have to be really smart because you have to figure out how to filter out all of the local interference because humans are extremely noisy in radio wavelengths. But once you figure that all out, all you have to do is sit there and wait. I mean, the other civilization is doing all the work in sending this message to us, and all we have to do is receive it. So it seems an extremely cost-effective way to at least do the very basic thing of listening for a signal. And plus it would be the most impactful discovery of all time. I mean, like you say, microbes on Mars are one thing, but alien civilizations, that's a whole other ballgame. I mean, that's a completely different change of mind that we would go through. I will add that when I was walking around in the Atacama Desert noticing these little communities that were living under these translucent rocks, the first question I had was whether there could be quartz on Mars. Because if there's little pieces of quartz on Mars, there could be these same exact communities living there. And because the Atacama Desert and Mars are very similar in how wet they are, although the Atacama Desert is much warmer and Mars is pretty darn cold. But Mars has some parts of it that are not that cold, actually. So if there's quartz on Mars, we could be go for that kind of community. But it turns out that in order to get quartz, you have to have basically plate tectonics and water. So unlikely, but Mars keeps defeating me. But yeah, if that answers your question.
Any more questions? Yeah, question in the back. Tim.
So this question expands the spatial scale a little bit, but I think most of us have heard that the universe is expanding, and I've just always wondered if the universe is expanding, what is it expanding into? How do you think about that?
Well, it's not expanding into anything. I don't know that we're really equipped to think about this. And I also don't know that there are some things that I sort of, after asking that same question for long enough, have thought that maybe we do, until we're at a point where we really can abandon reality as we know it in our conceptions of things, maybe we don't have to understand, maybe we don't have to have a picture that really is accurate. But the universe is not expanding into anything. The universe is everything that there is, and so there isn't anything outside of it. And that is a little counterintuitive when you imagine that everything in the universe used to be compressed down to a single tiny little point that would fit on the head of a pin and then exploded and expanded. But space itself is not an empty thing. It really is part of the fabric of the universe. You should think of space as a fabric. And the universe is, we're learning that the universe is not just expanding, it's accelerating in its expansion. It's what we call an open universe, not a closed universe. A closed universe would eventually stop expanding and then reverse its expansion and contract and go back down to being a single little point again. And that it would be of a finite size. But an open universe is apparently, quite possibly infinite in size. So the amount of the universe that we can see right now is only limited by the fact that it takes time for the light of other objects to travel to us, and the universe is only 13.5 billion years old. So that means the farthest away things we can see are 13.5 billion light years away. Doesn't mean there isn't a whole infinite bigger universe far beyond that will gradually come into view over time as the light arrives to us. But my current understanding is that the universe really is infinite in extent, and that it is expanding, though, that in that things inside of it are, space is stretching out and things are getting, far more and more space in between them. But it's not expanding into anything.
We have another.
But following up on that, what about the notion of the multiverse that Neil brought up in his Cosmos series?
I'm gonna have to go watch his show now.
Yeah.
Well, I don't know if, so I guess there's different ways to have a multiverse, and you could imagine if you defined our universe to be as far as one could possibly see based on how far light has traveled since the beginning, then there would be infinitely many other universes, just depending on where you're located. No two people are going to live in the same exact universe because you're in a slightly different place, and so you can see, a little farther in that direction and not as far in this direction. The interesting thing to me about that is this notion that there are only so many ways to arrange all of the atoms in this room. For example, we're all made of little atoms in the air and everything, and there's only so many ways to arrange them. And if you have infinitely many rooms like this, sooner or later, you're going to encounter another one that's arranged exactly the same way because there's only so many different ways to do it. And so that means there's another room out there somewhere, maybe very, very far away, where we're all sitting there having this conversation. And maybe I answered the question a little differently, but other than that, there we are. I can't comment more informatively than that, but I wonder if anybody else really can either.
Okay. Do we have one more question? I think we have been overwhelmed.
Me too.
Thank you so much, Maggie. This was just absolutely fabulous.
Thank you. Thanks a lot.
Yeah, that was really great. Thanks so much to Maggie Turnbull. Thanks also to the Minocqua Brewing Company and to our other sponsors. Remember, our next Science on Tap will be next September, and we'll certainly let you know what the date is, the 3rd or the 10th, with Ron Eckstein. And don't forget about our mining forum, Thursday, June 5th. Thank you all for coming, and please sign up for email reminders, and please print clearly. Thank you very much. Thank you, Maggie.
Thanks.